Okay, good morning. Welcome back. Happy Wednesday. Today is March 8th. We are covering our second of 2 days on improper integrals. Today we're going to tackle something called the comparison test. I'll remind you, last class we did a bunch of improper integrals. Remember, those are the ones where there's an infinity as one of the limits of integration, or the function inside of the integral blows up to infinity someplace in the interval, right? And so we tackled those last class, but in each case from last class, we were able to do an antiderivative, right? Every integral I gave you last class, you started the process by doing an antiderivative. Today we're going to tackle improper integrals where we can't do an antiderivative, but we'll still be able to make some conclusions. So that's what we're after today. Coming up after today's class is our long stretch of applications of integrals. So that's where we're headed. Quiz number 4 is going to be due next class. I will hand it to you today. It's another take-home quiz with the usual rules about, you can use a reference sheet of your own creation, but that is all. And hopefully you're making some progress on project 4, which is going to be due Monday coming up. Any questions on the calendar? Okay, so let's take a look again, starting on page 25 in the packet. Okay, today we'll be able to determine whether an improper integral converges by comparing it to another integral whose convergence behavior we know. Today is also the first of several days where we'll learn to write proofs, our first mathematical proofs this semester. Okay, so we're going to skip over number 1 and just remind you of the conclusion that you made in the activities in number 2. This is from last class. You guys did the integral from 1 to infinity of 1 over x to the p. You remember that? Integral from 1 to infinity of 1 over x to the p. And you made a conclusion based on doing 3 examples of this. If p is greater than 1, then that integral turned out to be some finite value, right? And so we said the integral converged. And if p was less than or equal to 1, then the integral diverged. It was infinite, okay? All right, and then you went the integral of the same thing, but from 0 to 1. Where's the problem here between 0 and 1? 0, because at x equals 0, this function is undefined. There's a vertical asymptote. That's why there was an issue. And you proved the following, that if p was less than 1, then that integral converged, meaning it had a finite value. And if p is greater than or equal to 1, the integral diverged. I do want to point out the conclusions here are opposing, right? Here, the first one, it converges when p is bigger than 1. And the second one, it converges when p is less than 1. So you got to make sure you're clear. Are we going to the infinity part, or are we going to the 0, right? 2 different issues. Okay, so let's develop a theorem right here, number 3. Suppose that f and g are both positive functions, and that g is at least as big as f for x sufficiently large. Take a look at this picture right here. G is it's going to be the thin line on your paper, and f is the bolded line on your paper. For me, g is purple and f is blue, okay? So in this case, would you guys agree that g is at least as big as f starting at x equals 1? That's where they meet each other. And then for the rest of eternity, g is bigger than f, okay? All right, suppose that we know that the integral from a to infinity, a is going to be 1 in this case. Suppose that we know that g converges. That means that the area under g, if that integral converges, that means the area under g is what? Finite or infinite? Finite. That's what converges means. So we're assuming right now that the area of this green thing forever is some finite number. What can you conclude about the area under the blue? Is it finite or is it infinite, or are we not sure? It also has to converge. It has to be finite because it's smaller than that green number, right? And if green is some finite value, then red is definitely finite as well. Agree? Okay, so then we can write that as our conclusion here. Then the integral from a to infinity of f of x dx also converges. Okay, now we're going to go the other direction. Let's take a look at the area under f again. That's the bottom one here. Suppose that you know that this is finite. What can you say about the total area under G? Is it definitely finite? Is it definitely infinite? Or are we not able to tell? What about the area under G? Yeah, Josh? Not able to tell because the area under G is bigger than the area under F, right? And that red stuff is finite, and so we're bigger than some finite number. It could still be finite, but it might be so big that it's actually infinite. So having that red area be finite, we can draw no conclusions. Similarly, if I told you that the green area that's under the G function, if I told you that that green area is infinite, then what can we say about the area under the lower function? Nothing. We can't say anything because it's smaller than this infinite thing, but it could still be infinite, or it could be finite. But there is one case, one other case besides this one we've written, where we can say something concrete. Suppose the area under this lower function is infinite. What can you say about the area under G? Also infinite, because it's bigger than this infinite area that's up here, okay? All right, so let's write our conclusion down here. Suppose that you know that the integral under the F, that was the bottom one, diverges. That means the area is infinite. What can we conclude? We can conclude that the integral of g of x also diverges. And these two statements that we've got up here now are together called the comparison test. It's an appropriate name. We're comparing one function to another, right? And we're going to make sure we refer to it by name whenever we use it. So on the next page, we've got our summary. We could show an integral converges if we can find a larger convergent integral. And we can show an integral diverges if we can find a smaller divergent integral. So we're going to be playing around with inequalities today. In practice, what we do is try to figure out a simpler function than the one in question, but with similar end behavior, and then we'll compare. Let's try number 6 here. Use the comparison test with our big conclusions to decide if each of the following integrals converges or diverges. So the first integral, from any number up to infinity of 1 over e to the 2x. 1 over e to the 2x. Let's just think for a second about the graph of 1 over e to the 2x. 1 over e to the 2x, you guys agree is the same as e to the negative 2x? Is that an exponential growth or an exponential decay? That's an exponential decay, and we know exponential decay functions look like this, right? So there's the graph. And we're going from any number over to infinity. I'm just going to put my generic number here, right? Any number to infinity. So we were thinking about that area, and we are trying to decide whether that area is finite or infinite. Okay, so 2 ways to tackle this one. Way number 1, we could have done last class. You could just find an antiderivative, can't you? Right? E to the negative 2x, that's just going to be a u substitution. You can find your antiderivative. You can change infinity to a b, take a limit as b goes to infinity, and get your answer. We're instead going to do option number 2, which is a comparison test. Okay, so let's start writing an inequality here. Let's make up something like e to the 2x compared to x to the 17th power, just making up the 17. Which one, if x is really big, which one eventually dominates? Which one is bigger? X to the 17 or e to the 2x? We know exponential growth functions dominate polynomials, right? So for large x, e to the 2x is for sure bigger than x to the 17. Agree? And we don't need to be super precise about how big x is. This is just informal. We know that exponentials at some point dominate any polynomial. Okay, I'm going to flip over both of these guys. I'm going to compare 1 over e to the 2x to 1 over x to the 17. You guys know whether that inequality changes or flips direction? Anna says it gets flipped. What do we think? Let's just do a simple example. We know that, so on the left-hand side, e to the 2x, I'll just make up a number. I'll say that that's 15, and it's bigger than 14, right? And so if I compare 1/15 to 1/14, which inequality symbol goes? It changes, right? 1/15 is a little bit smaller than 1/14. So this is true. Anytime you have positive numbers, you flip over both sides, the inequality changes direction. So we've got that. Okay, so what that means is that our integrand, this 1 over e to the 2x, at some point is smaller than 1 over x to the 17. Again, I just made up the 17. Could have picked any number up there that was bigger than 1. Okay, that's fine. So what does that mean? Well, let's consider one other integral. It's related integral, 1 over x to the 17 dx from some number up to infinity. Well, let's leave it as a 1 here. From 1 up to infinity. Take a look at the big conclusion on the previous page. What can you say about this integral right here? This is a 1 over x to the p, right? In this case, p is 17. So yeah, this 17 is greater than 1. So what's the conclusion? This integral converges. This integral converges, the first row. This integral here converges since p is 17, which is greater than 1. Right? That was our big conclusion from last class. And now it's just one last step to bring this back to our original integral. 1 over e to the 2x is smaller than 1 over x to the 17, and the integral of 1 over this x to the 17 converges. So what can you say about our integral, the original? Does it converge or diverge? It converges. It is smaller than something finite. So that's our conclusion. So integral 1 over x, 1 over e to the 2x from any number up to infinity converges by the abbreviated CT, comparison test. Feel free to make that same abbreviation. That's the comparison test. We compared our integral to one whose behavior we know, and the inequality worked out in the right direction, so we get our conclusion that our integral behaves exactly the same as the integral of 1 over x to the 17. Okay, let's take a look at the other one. I'm actually going to skip, just in the interest of saving some time, I'm going to skip the write-up for this one. We'll have a chance to do one that diverges in just a minute on the next page. But it turns out this integral here, I'm just going to write the conclusion. You'll get plenty of practice to write up all the details of the comparison test. So we're going to skip that one, but e to the negative 2x turns out to diverge. And so the cutoff in this case, if I'm making a big conclusion down here at this bullet point, e to the ax, do you have a guess where the cutoff is between the convergent values of a and the divergent values of a? One over e to the 2x converged, 1 over e to the negative 2x diverged. Josh? That's it. It's just positive or negative. So if a is converges if a is bigger than 0, and diverges if a is less than 0. Okay, so we now have 3 sets of useful integrals for comparison. The first 2 we talked about on the previous page. The last one is this new one here that we just wrote down. Is about 1 over e to the ax. It converges if a is bigger than 0, and diverges if a is less than 0. We're going to use all 3 of these over and over again, and we'll get used to them as we use them more. Okay, so on the very next page, we're going to determine the convergence or divergence of these 2 integrals. First one, integral of from 1 to infinity of 4x squared over x to the 4 plus 4x plus 1. Okay, so first of all, I want to observe that we could not use the technique from last class because I don't know how to do an antiderivative of this thing. I would try U substitution, I would try partial fractions, neither of them would work, and I'd be stuck, all right? So we cannot use the directly find an antiderivative technique. Instead, what we're going to do is compare. So the goal here is just to determine whether this integral converges or diverges. All we care about is it finite or is it infinite? If it's finite, we're not going to know what it actually converges to. Does it converge to 10? Does it converge to 500? I don't know. I don't care. All I need to know is whether it's finite or infinite. Those are my two choices. Okay, so first thing we need to do is figure out what this thing maybe behaves like. We're going to try to compare this to some simpler function that's in that list on the bottom of the previous page. So first of all, what can I pull out of the integral? The 4. 4 is a constant multiple, right? So I'm going to bring that 4 out. Always bring my constant multiples out just to make the integral simpler. I still can't do the integral, but it's simpler. And then I'm going to ask myself, okay, looking at the denominator, which of these three terms is the most important one for large x's? X to the 4th. The leading term we know like dominates the other ones, right? So I'm going to compare to x squared on top, that's the only term up there, and x to the 4th on the bottom. Now, it's not okay to just ignore the 4x and the plus 1, but if x is really big, then adding 4x and adding 1 to x to the 4th is going to make hardly any difference. Not even going to be a drop in the bucket, right? X to the 4th is so much bigger than the other two terms that it essentially boils down to just x to the 4th on the bottom. And the reason this is helpful is that I can simplify and get 1 over x squared. Say, hey, I actually can tell you something about the integral of 1 over x squared. Okay, so all right, another abbreviation we're going to start using here. UIC, useful integrals for comparison. That's what we called the 3 bullet points on the previous page. Integral from 1 to infinity of that last green thing over there, x squared dx. How much is p in this one? Or first of all, which bullet is this? The first, the second, or third? Take a look on the previous page. Is this the first, second, or third bullet? Is it the first, second, or third bullet? That's the first one. 1 to infinity, that's the first one. 1 over x to the p. How much is p? It is 2, which is greater than 1. So this integral converges. So we're going to write it as a complete sentence here. By the useful integrals for comparison, this integral converges since p is equal to 2, which is greater than 1. Right? Full sentence. Has lots of details in it. No, we don't know what it converges to. But that's okay. Okay, so I've got a convergent integral that I think is similar to the original integral that I'm asked about. What am I really hoping in terms of the inequality? Do I want this original integral to be more or less than this convergent integral down here? Which direction is helpful to us? We want ours to be more or less. Less. Need it to be less. If our integral happens to be less than this finite thing, then our integral is also finite, right? It's smaller than a finite number. If our integral happens to be more than this finite thing, that was one of the cases where we can't draw any conclusions, right? So we're really hoping that the inequality goes in the right direction, that our integrand is less than this one. Okay, let's give it a shot. Let's start by comparing denominators. X to the 4th plus 4x plus 1. How does that compare to the simplified denominator where I only looked at the leading term? What inequality goes in between? Greater, right? We're adding positive stuff over there. But I want these guys to be in the bottom. So we're going to put a 1 on top of each of these. What happens to that inequality in between? Changes, right? Changes direction. So it becomes less. That's kind of a happy moment right there because our integral is starting to look like maybe it's less than the 1 over x squared. Okay, what did I want on the numerators here? 1x squared. So I'm going to multiply both of these things by x squared. Now remember, there's something funny that can happen when you multiply an inequality. What kind of number flips the, is multiplied by negative will change the direction, right? But what can you say about x squared? So it's always positive. So I'm multiplying by a positive thing, so that direction stays exactly the same way that it is. Therefore, you guys know the three dots, meaning therefore? So therefore, x squared over x to the 4 plus 4x plus 1 is greater, nope, stays the same direction, less than x squared over x to the 4. And that's equal to our 1 over x squared. The 4 is going to multiply, well, we'll make our conclusion here and then we'll talk about the 4. Okay, does the direction go the way we wanted? Our integrand is smaller than 1 over x squared. Is that the direction we wanted? It's exactly the direction we wanted. Okay, so by the comparison test, what can we say about the integral of x squared over x to the 4 plus 4x plus 1? 1 to infinity. Converges or diverges? Converges. It also converges. I'm even going to get the word also in here because I'm saying it does the same thing as this 1 over x squared integral up here. Also converges.
So if it was greater than we wouldn't know.
We wouldn't make any conclusion. Yeah. But you can trust that I'm going to give them to you in the direction that's going to work. Yeah. Okay, what about Nick's question? Nick says, how about the 4? Well, we know this integral converges, which means this integral is finite or infinite? Finite, right? So if I multiply this finite number by 4, what kind of a number do I get? A finite number. I'm just going to tack the 4 right in there, right? Multiplying by any number makes no difference when the only answers, the only possible answers are finite or infinite. Okay, so 2 observations here. I've kind of said this before already today. This is an integral that we could not do. We could not find an antiderivative of this thing from the beginning. So it is a tougher problem for us. The question that we answered is a weaker question. We didn't say this thing converges to, 72. I don't know what the actual area under the curve is. All I know is it's finite. So you give me a harder problem, I'm going to make a weaker conclusion, right? Last class, I wanted to know not just is it finite or infinite, but if it's finite, what's the value? What's the number? This class, finite or infinite, that's all. Okay, let's take a look at part B here. I'll try to tackle this one a little bit quicker. Integral of 2 to infinity of the cube root of x squared minus 1, 8 over that thing. Okay, u substitution isn't going to work here. I feel like maybe a trig sub is something to try, right? I see an x squared minus 1, so maybe a trig sub. It turns out I don't think anything is going to help us in this one. I don't think we can do an antiderivative here. So let's see if we can start comparing. First of all, what can we pull out of this integral? 8. So copy everything else, pull the 8 outside. And then we're going to just start a new thought over here. I'm going to compare, how did we write it upstairs? We just said compare to, okay. So I'm going to compare to, okay, I'm just trying to make this thing in the integral as simple as possible, but still similar enough to what's currently in there. Okay, the one on top, we're not going to get any better than that. I've got a cube root. I've got an x squared. What have I done? What have I ignored? The minus 1, right? And again, it feels kind of wishy-washy to just ignore minus 1. But if x is really huge, and that's where the problem is, right? When x is really huge, subtracting 1 from x squared makes hardly any difference, right? Talking about the difference between like 1,000,001 and 1,000,000. It's pretty much the same thing. Okay, so we're going to compare.
Quick question. If
Yeah.
it wasn't an interval, let's say 0 to infinity, would we still be able to take the 1 out as x1?
Yeah, so if this goes 0 to infinity, then we've got two problems. One problem is at infinity, what's the value of x that makes this denominator 0? X equals 1 is a problem because this fraction is undefined. So this integral we would actually have to separate into two. We'd have to go from 0 to 1 and then from 1 to infinity and deal with the 1 and deal with the infinity separate. That's why to avoid that problem, I put a 2 there to make it bigger than 1. Yeah. Okay, so we're going to compare it to this guy. That means that we're looking at the integral, same 2 to infinity, but of that green thing, 1 over the cube root of x squared, right? So I first want to try to make some conclusion about this integral, and then I want to try to relate this integral to the original one. That's always the process here. Okay, let's write this as 1 over x to a power because we've got some fancy properties. What's the power? 2/3, right? Cube root x squared becomes 2/3. And lo and behold, this is one of our useful integrals for comparison on the previous page. Is this the first, second, or third bullet? It's the first one because we're going from number up to infinity, and it's a 1 over x to the p. Yeah. Okay. This integral right here, let's see, which diverges by the useful integral for comparison, and we'll just put parentheses here. How much is p? Yeah, all right, I'll keep it as 2/3. The magic cutoff between the convergent and divergent is what number? Is 1, and in this case, p is less than 1. Okay, so we know something about the simpler integral, it diverges. What are we really hoping about our integral? Do we want it to be more or less than this divergent one? We want it to be more because divergent means infinite, right? There's infinite area. If ours is bigger, then ours must be infinite too. So that's like we're crossing our fingers here. We have no control over which way the inequality goes. Okay, so let's write the inequality. I'm going to again start with just comparing the denominator of the original to the denominator of the simpler one. Cube root x squared minus 1 compared to cube root x squared. I'm really hoping it's obvious to you which inequality goes in there. Greater or less? Which one goes in? Less, right? Because we subtracted 1. So the left-hand one is smaller. But I didn't want these upstairs. I wanted them in denominators. So we do 1 over. This is our standard flipping trick. What happens to the inequality? It changes to greater. Which means that our integrand, our integral, is bigger than this divergent integral. Was that the direction we wanted? You bet, right? The divergent one has an infinite area. Ours is even more. So I'll write our concluding sentence here. So our integral, which was 1 over the cube root of x squared minus 1 from 1 to infinity, what must it do? Converge or diverge? Also diverges by the, what was the name of the thing from today? So the useful integrals for comparison is what we used up here. But this thing right here is called the comparison test. So we had two different acronyms today. Useful integrals for comparison. And our conclusion today is always going to be a sentence involving the comparison test. Okay, and so I would suggest that the material today is quite a bit theoretical, more theoretical than a lot of what we do in this class. We do a lot of calculations. This is maybe the most theoretical kind of thing that we've done so far this semester. It's kind of heady stuff. I mean, we're using inequalities, we're ignoring stuff that isn't the leading term, And then we're comparing and hoping inequalities go in the right direction, and then using this comparison test. And, I mean, these are full-fledged proofs that we are writing, possibly for the first time. Okay, so really, really important to me that we kind of get the flow of the proof writing down. So I'll walk around, I'll be looking very carefully at the language that we use here, but raise your flag if you get stuck.